Hi, I'm Fabian Mühlberg and I'm presenting joint work with Ross Tate entitled Transitioning from Structural to Nominal Code with Efficient Gradual Typing. Now that title is already a bit of a mouthful, so let me start by explaining what all of those words mean. Here's a simple program that a programmer might start out with. It creates a record with initially a single method foo, though it might acquire additional fields and methods later through appropriate assignments. This code is untyped. There are no type annotations, which in gradual typing is equivalent to having type annotations using the special dynamic type din. Gradual typing allows us to replace some or all of these annotations with more concrete types to gain the benefits of static type checking. For example, we could specify that the method of our record always returns integers. Because the argument to the function is still typed as dynamic, we cannot statically guarantee that the returned value will indeed always be an integer. But gradual typing is optimistic and statically allows this program so long as an integer return value is at least plausible. However, in order for gradual typing to be sound, we have to insert a runtime type check here to ensure that whatever value is returned at runtime is actually an integer. Once we add a corresponding type annotation to the argument, this runtime type check can again be omitted, and the multiplication operation can be optimized to always expect integer operands. Now, given our record's definition, one might think that we could assign it a structural type indicating that it has an appropriate method foo. Unfortunately, even if we were to do that, we would not get much of a performance benefit. Knowing the structural type of an object, such as that it has a method foo, does not inform the compiler where the implementation of foo can be found in the object. As such, it still has to implement method dispatch using a hash table. All the structural type does is guarantee that the hash table lookup will succeed. On the other hand, if we were to refactor this into code using a nominal class, then the nominal type would enable the compiler to know that foo's implementation can be found at a fixed offset within the object's vtable. In this way, migrating code can involve more than just a shift in typing discipline. It can involve a shift in paradigm as well. And our work is the first to bridge this gap. On a higher level, here's the process we're envisioning, with the code shown before put into a bit more context. A programmer first writes a fully untyped structural piece of code. They may then introduce interfaces to describe the kinds of interactions in their program and use those interfaces to introduce some more concrete type annotations into their program, possibly in several steps. While the interaction of nominal interfaces with structural values, as shown here, is also a key contribution of our work, in principle, existing work in gradual typing supports all of the steps we have seen so far. Now one might switch paradigms and introduce a class to replace the original records. While we can obviously add more type annotations within nominal code, the state-of-the-art in gradual typing does not model the migration between the two paradigms. Our paper extends gradual reasoning to this transition, allowing programmers to migrate both between typing disciplines and coding paradigms. To this end, we present MonNom, an object-oriented language with a nominal type system and monotonic casts for structural values. To support the different paradigms, MonNom provides different kinds of values. First, there are the standard instances of nominal classes, just like in languages like Java. Besides these, MonNom also provides two kinds of structural values: lambdas, which just consist of a signature in the function body, and records, whose code is able to reference the particular instance, and who can contain arbitrary fields and methods, similar to class definitions. As for classes, method names may also be lambda. Values that have such a method can be invoked directly, just like a lambda value. A key to implementing runtime type checks efficiently is that MonNom's type system does not contain structural types. Therefore, while instances of nominal classes are typed with a corresponding nominal type, structural values are always assigned the dynamic type din. They can, however, dynamically acquire nominal interface types through casts. Since the types in MonNom are always nominal, there are two high-level cases for casts. First, a value might be cast to a class. This kind of cast only succeeds for actual instances of that class, not for structural values, which is important for efficiency, as class types let us access a value's members via compile-time offset calculations. This relies on layout invariants that structural objects do not generally satisfy. However, a value might also be cast to an interface. This succeeds for instances of nominal classes precisely when the class explicitly implements that interface, as is normal for nominal languages. However, it also succeeds for all lambda values and for most records. The only condition here is that if the interface prescribes a lambda method, the record needs to provide one. This is necessary for an optimized implementation of direct invocations. Structural values keep track of which interfaces they have been cast to, both in order to speed up future checks and in order to cast return values of typed method calls to the correct return types. This casting scheme is called monotonic, as the typing information ascribed to individual structural values increases monotonically. With that, let us look at some important aspects of code migration in MonNom. The key theoretical properties related to migration are called the gradual guarantees. Traditionally, the gradual guarantees are formalized to bridge typing disciplines, modeling the transition from less typed to more typed code, which is connected by what is called the precision relation, shown here for expressions. You can think of the left-hand expression as being less relaxed than the right-hand expression, meaning that on the left, there are more concrete type annotations than on the right. Now there are two gradual guarantees. The first one is the static gradual guarantee, and it requires that if a less relaxed program type checks, then so does any more relaxed version of it. The second one is the dynamic gradual guarantee, which requires that if a less relaxed program executes successfully, then so does any more relaxed version. Together, they guarantee that if a valid type assignment for a program exists, adding the corresponding type annotations neither changes the typability nor the semantics of that program. Now, in MonNom, we not only need to bridge typing disciplines, but also coding paradigms. This means that in judging whether one expression is a relaxation of another, we need to take into account the overall programs that they are part of. This means that the static gradual guarantee needs to be reformulated to take context into account, now stating that if a less relaxed expression type checks in some program P, then a more relaxed version of that expression must type check in a relaxed version of P. Similar reasoning applies to the dynamic gradual guarantee. To see how the precision relation models program migration, let's look at two examples. First, consider the precision rule for let expressions. What we see here is actually the standard precision rule for let expressions as used in previous work. This kind of precision relation almost always simply operates pointwise on the components of an expression. The only interesting relationships are on the levels of types. The relevant premises do not change when adding the program contexts we need for our cross-paradigm model. However, for this rule, we need to add an additional premise, namely that the type in the more relaxed expression must be valid in the more relaxed program. This is important because our notion of program migration allows us to add new classes and interfaces. Therefore, a more relaxed program might not contain the class or interface that some type in the less relaxed program is referring to. Secondly, the precision relation also models replacing structural values with instances of nominal classes. It's just that because not all structural code can be turned into nominal classes, the direction of reasoning feels a bit inverted. In order to model the transition, we first need to look up the class definition in the more precise program, which gives us access to its definition. The let expression in the conclusion is effectively for inlining the class's constructor. Therefore, we need to make sure that the argument type of the constructor is relaxed in the right way and makes sense in the relaxed program. And of course that the argument expressions are related via precision. Now we can check that the body of the let expression is a relaxation of the structural value that mirrors class's body. Finally, we need to ensure that the class is actually not defined in the relaxed program. This is because otherwise the relaxed program could contain a cast to that class, which because of the way we defined casts would fail for the structural value and therefore make the difference between nominal and structural values observable. This effectively means that all structural values that should be replaced by instances of the same class need to be migrated at the same time, which we believe is reasonable. Aside from being able to satisfy the gradual guarantees, our second major design goal was allowing for an efficient implementation. We already saw some restrictions we imposed on the language design to accommodate this goal, but let's look at some more details. In untyped code, we fundamentally do not know what kinds of values we are passing around, and therefore what size they might have. So, all values passed around in MonNom are 64 bits wide. Typed code can rely on static type information to access the raw versions of primitive values, that is, integers and doubles. Untyped code needs to resort to standard bit tagging techniques to avoid having to allocate heap objects for such primitives, at least in most cases. These differences in representation are especially important in dynamic method dispatch, where we need to make sure that values are passed around in the expected representation. The technique we discuss next greatly helps with that. To support imposing interfaces onto structural objects, we use a technique we call call tags. These are an extension of an existing technique to support efficient interface method lookup called interface method tables. An interface method table is essentially a small hash table whose keys are combinations of interfaces and methods. These keys are also our call tags. The entries in the table are functions that, in addition to the receiver of a method call and the normal arguments, also expect to be given the call tag. A nominal class simply uses the call tag to find the method implementation that implements the particular interface method combination. Structural values also provide an interface method table, but their entries are simpler. They just tail call the call tag with the given arguments. This is possible because call tags are not just identifiers, but really function pointers that also serve as identifiers for interface method pairs. The function they point to takes care of the structural function lookup, representation conversions, and return type casts, all in an optimizable manner. This way, typed code can execute interface method calls just as in any standard nominally typed language using the interface method table technique, and structural code can also handle them reasonably efficiently. How efficiently? To answer this question, we ran some experiments, which we set up in the standard way for gradual typing benchmarks. For each program, there is a fully typed, and in our case also fully nominal version, and a fully untyped structural version. From the latter, we can move towards the former by adding type annotations, or in our case, also by adding interfaces or turning records or lambdas into classes, in various orders. This creates a lattice of intermediate versions between our two extremes, with each step getting us closer to the fully typed version. We run all the intermediate versions we generate and plot the running times. Ideally, type annotations enable optimizations, making the program faster as we get closer to the fully typed program. However, we also need to insert runtime type checks whenever typed and untyped code are mixed, so we can expect some overheads in intermediate configurations. In previous work, these overheads have sometimes become quite excessive, with intermediate programs taking several times the running time of the fully untyped program. Now to our benchmarks. Intersort is a benchmark we designed to evaluate the effect and intermediate overhead of the new paradigm shift we support. Its main data structures are a doubly linked list and its nodes and iterators, for which we also specify nominal interfaces using a generic type parameter. These data structures are transitioned from structural to nominal code. The program itself applies quicksort to such a list of 100,000 integers. The black axes on the chart mark the running times for the various MonNom configurations. While there are some configurations with higher overheads, there is a clear downward trend for most configurations as we add types. We implemented the same program in Java, C# and JavaScript, and find that MonNom's fully typed version performs about as well as those industrial languages. We also implemented the benchmark in more academic, gradually typed object-oriented languages, namely Higgs-check and reticulated Python, which, as you can see, do not improve performance with increasing typedness. We also implemented benchmarks we took from existing work, but which was less geared towards object-oriented languages. MonNom again performs well in several cases where other gradually typed languages don't. You can find the details in the paper. To summarize, gradual typing is not only useful to describe the migration between typing disciplines, but can also model larger changes to a program, for example, the migration between coding paradigms. To demonstrate this, we presented MonNom, a language that we co-designed to both satisfy the gradual guarantees and allow for an efficient implementation, in particular of the runtime type checks necessary for sound gradual typing. Now, in our paper and technical report, you can find more details on our formalization and the guarantees and their proofs. You can also find more details on the benchmarks that I presented earlier. We also have an artifact which contains the complete source code for the MonNom toolchain and our benchmarks. And the implementation provides a lot more features than have been formalized in the paper. With that, I hope that you have a look at our paper and artifact, and in the meantime, thank you for watching.